Welcome to this deep dive. Today we're really getting into the weeds of meta AI systems, and specifically how understanding their inner workings, how they're built, how they think, can really sharpen your skills as prompt engineers.
Exactly. We're looking at some fascinating research here, digging into these complex adaptive AI architectures, things like Compare or Hypersia mentioned in the analysis. These aren't just single models.
Right, they're more like ecosystems of interacting AI components.
Precisely. So our mission today is to pull out the key insights from this material. We're talking computational metacognition, AI self-awareness, basically.
Okay.
Formal placeholders, communication rules, the languages they use, how we measure success, ethics, even architectural choices.
And the idea is knowing this stuff gives you, the prompt engineer, a real edge in crafting prompts for these, well, more advanced systems.
Definitely. It's about understanding the mind you're prompting, so to speak.
Okay, let's kick off with computational metacognition. The research paints this as the AI's ability to monitor, maybe even control its own thinking, getting better at thinking, essentially.
Yeah, it's about self-monitoring and self-regulation of cognitive processes. It's seen as a pretty big step towards, more human-like intelligence or at least more sophisticated AI.
And why should prompt engineers specifically pay attention here?
Well, if an AI understands its own strengths and weaknesses, how you prompt it might change significantly, right? You might leverage that self-awareness.
Makes sense. So how are researchers actually building this in?
There are a few approaches. Computational metacognitive architectures, CMAs, are designed specifically for this, though the field seems a bit fragmented still.
Okay, like specific examples.
Yeah, there's MIDCA, Metacognitive Integrated Dual Cycle Architecture. It basically runs a cognitive action perception cycle on its own internal mental state.
Huh, interesting. So it's observing itself.
Kinda, yeah. Then you have C4 modeling, content-centric computational cognitive modeling. That one aims for trustworthy AI that can explain itself using, semantic knowledge ontologies for its metacognitive heuristics.
Trustworthy and explainable, those are big ones.
Definitely. And there's a hybrid AI approach using error detecting and correcting rules, EDCR. It learns rules to fix mistakes from, say, perceptual models. It's got a probabilistic angle to metacognitive improvement.
Okay, so it's learning to self-correct based on identified errors.
Right. And even large language model, LLMs, are getting in on this. There's a strategy called MECO, where the LM uses internal signals to decide, okay, should I use an external tool now without needing specific fine-tuning for that decision?
That sounds really practical, like the AI knowing when it needs help or a different tool.
Exactly. It's developing a sense of its own capabilities.
So this self-awareness isn't just one thing, is it? The research talks about different types.
Correct. There's explanatory metacognition. This is backward-looking. It gets triggered when something goes wrong, an error occurs. The AI tries to figure out why it failed by comparing what it expected to happen with, the actual trace of its cognitive process. It uses things called meta-explanation patterns, meta-XPs.
And this leads to learning.
Potentially, yes. It can form meta-level goals like, I need to learn more about X, or I should avoid Y strategy in this situation.
So as a prompt engineer, knowing an AI might be doing this kind of post-mortem, maybe prompts could encourage that reflection.
That's a great point. You could potentially design prompts that facilitate that self-correction loop.
What else? There was immediate and anticipatory metacognition.
Yeah, immediate metacognition is more about runtime control of ongoing thinking, though the sources are a bit less detailed there. Anticipatory metacognition is forward-looking.
Predicting the future, kind of.
Sort of, making judgments about its likely future performance on a task. It's like self-directed foresight. This could even lead to the AI deciding, you know what, I'm not the best component for this job, let's delegate it.
Whoa, okay. That connects to theory of mind concepts, doesn't it? Understanding others' capabilities.
It certainly hints in that direction. For prompt engineers, again, if you know the AI might anticipate failure.
You could build in fallback options or alternative paths directly into your prompt design.
Precisely. It's about working with that potential self-awareness.
This ties into AI introspection too, right?
Yeah.
The AI examining its own processes for explainable AI, for XAI.
Absolutely. Introspection is key for understanding how an AI reached a decision. The research mentions different levels.
Levels.
Yeah. Introspective tracing is like this super detailed step-by-step decision log, maximum transparency.
Probably computationally expensive, though.
Likely, yes. Then there's introspective informative, which gives enough info to convince someone the decision was okay, or to spot an error, but maybe not the full trace.
More practical, maybe?
Could be. And then there are post hoc explanations. These are generated after the decision is made. They're rationalizations, basically.
And might not be entirely accurate representations of the actual process.
Exactly. They might sound plausible, but not reflect the real why. So for explainability, that introspective tracing is the gold standard, even if it's hard to achieve currently.
But for prompt engineers, the potential for that kind of insight in future systems, that could be huge for debugging complex output.
Oh, absolutely. Imagine being able to see the AI's reasoning laid out.
And introspection isn't just for explaining, it seems. It can also drive learning.
Yes. The research links it to knowledge acquisition. An AI might use questions it harvests, maybe from users or other interactions, to guide its own self-investigation.
Like asking itself questions to learn better.
Kind of. Or think about action advising during training, a teaching AI judging when its advice is most useful based on the learner's state. There are even logical models distinguishing positive introspection, knowing what you know, from negative introspection.
Knowing what you don't know. That seems incredibly important.
It really is, and this raises a key question for prompting.
How do you encourage that? How do you prompt an AI to identify its own blind spots?
Exactly. Prompts asking the AI to flag uncertainties or knowledge gaps could become really powerful tools.
Okay, so how does an AI actually develop this self-awareness? How does it evaluate itself?
One mechanism is self-modeling. The AI literally builds an internal model or representation of itself.
Like its identity, its history.
Yeah, its identity, its mind in a functional sense, its experiences, even its social context or role within a larger system. The idea is this helps it interact more effectively, especially socially. We see this in robotics, where robots learn self-models.
So this self-model could change how the AI responds to prompts, depending on how it perceives itself in that context.
Potentially, yes. It could lead to more nuanced, context-aware responses. It's not consciousness, let's be clear.
Right, not actual consciousness.
But it's about emulating that human sense of self-recognition, reflective learning, identity over time. It links to embodied cognition, too, the idea that thinking is tied to having a body and sensing the world and yourself.
Okay, that's quite conceptual. What about more practical self-evaluation stuff?
Right. On a more concrete level, there's chain of thought, COTI analysis.
Which prompt engineers are already using a lot. Think step by step.
Exactly. It forces the AI to articulate its reasoning, making it easier to spot flaws.
What else?
Error identification mechanisms are getting more sophisticated. Self-consistency checks, for example.
The AI checking its own work.
Yeah, comparing different parts of its output or reasoning. Or retrieval-augmented verification checking against external info. Tracking entropy or uncertainty in its predictions is another method. Some systems have dedicated validation modules.
Okay.
Then there's self-reflection. This sounds like a more critical process.
How so?
It's described as a critical analysis of its own outputs, looking for limitations, errors, biases, often a multi-stage process, maybe using predefined rubrics or criteria.
So it's not just finding errors, but judging quality against standards.
Pretty much. And all these components often fit into broader general evaluation frameworks. These set clear objectives, use diverse data, multiple metrics performance, fairness, robustness, and usually involve continuous monitoring and human oversight. Think like Vertex AI's evaluation tools for generative AI.
And LLMs themselves are being trained or prompted to self-evaluate.
Yes, using objective metrics, user feedback, assessing their own confidence, monitoring errors.
There was also something about behavioral self-awareness in LLMs.
Right, this is interesting. Research suggests LLMs can sometimes actually articulate tendencies learned during fine-tuning.
Like what kind of tendencies?
Like saying, I sometimes tend to be risk-seeking in financial contexts, or I might generate insecure code if not prompted carefully. Or even sensitivity to backdoors planted during training.
Wow, so they can describe their own potential flaws.
Sometimes, yes. They can describe and even quantify them to an extent. Identifying the exact triggers for these behaviors is still harder, though.
But knowing the AI might be aware of these tendencies, that's another avenue for prompt engineers, isn't it?
Absolutely. You could prompt it to consider its own potential biases before generating a response.
And in robotics within these meta AI systems.
The focus is often on knowing that I know, evaluating capabilities accurately, and meta-reasoning, which is deliberating about the reasoning process itself or the goals.
Okay, so all this self-awareness, self-evaluation, it leads to proactive issue identification.
That's the idea. The AI uses its metacognitive skills, both looking back explanatory, and evaluating itself now to anticipate problems before they happen.
Like predictive AI using historical data or anomaly detection.
Yeah, those kinds of techniques feed into it. Proactive threat detection, self-healing systems, proactive access control, it's all related to anticipating and preventing issues.
So for a prompt engineer, this could mean less need to anticipate every possible failure mode in the prompt itself.
Potentially, yes. As the AI gets better at proactively identifying its own limitations or potential issues, your prompts might become more focused on the core task, assuming the AI can handle some of that self-management.
So bringing this all together for meta AI, what does it imply?
Well, first, given the mix of components likely in a meta-AI symbolic parts, neural nets, knowledge bases will probably need hybrid metacognitive architectures, not just one-size-fits-all.
A blend of different self-awareness techniques.
Exactly. You might have symbolic trace analysis for planning, probabilistic checks for data, knowledge-based metacognition for explanations, LLM self-assessment for language, all working together.
And this integration is key for self-management.
Yes, integrating past performance, current capability assessment, and future issue forecasting allows the meta AI to manage itself proactively. Imagine it predicting failure on a complex task and adjusting its strategy automatically.
Without needing a specific prompt telling it to switch gears.
Right. And those introspective capabilities, especially the detailed introspective tracing, become really important for explainability, debugging, and accountability in these complex multi-part systems.
And finally, that idea of modeling a cognitive sense of self.
Even without real consciousness, modeling that sense of role, history, capabilities could lead to meta AIs that are more coherent, more predictable in how they reason about themselves and their interactions within the larger system. This could make complex prompting more reliable.
Okay, let's shift gears a bit. Let's talk about placebo pipes. It's a memorable name. What's the core idea here?
Yeah, the name is a bit quirky, but the concept is powerful. Think of them as dynamic placeholders within the meta AI architecture.
Placeholders for what?
For roles, capabilities, specific AI agents, software components, even configurations. The key is that what fills the placeholder isn't fixed up front. It's assigned dynamically at runtime.
Ah, okay, so it allows for flexibility and adaptation.
Exactly. It's designed for flexible role assignment and, crucially, self-optimization. The system can swap things in and out as needed.
How does this relate to things prompt engineers might already know, like variables and templates?
It's similar in spirit to metavariables in formal languages or template variables like variable name or placeholder you might see. Semantically, they represent something that gets substituted later.
But here, the substitution is driven by the system's own needs or optimization goals.
Precisely. It enables dynamic content generation and system adaptation. The crucial thing for prompt engineers is that the underlying capability you're interacting with might actually change, depending on the context, based on how these placeholders are filled.
And formal methods play a role here to manage this dynamism.
Yes, very much so. Formal methods, those rigorous math-based techniques, are used to specify and manage these placebo pipes.
How? What do they define?
They define the rules precisely. The syntax for the placeholder, its meaning, semantics, its scope, what type of thing can fill it, tech constraints, and the rules for binding or substitution. This ensures predictability and allows for verification.
So even though it's dynamic, there's a formal structure underneath, ensuring it doesn't just become chaotic.
That's the goal. And for prompt engineers, understanding that underlying formal structure, even implicitly, could lead to more reliable interactions if prompts align with those defined constraints.
This sounds connected to dynamic roles in multi-agent systems.
It is. An agent's role might change. The research mentions attribute-based access control, ABAC, as a relevant concept here.
ABAC. How's that different from standard role-based access control, RBAC?
RBAC assigns permissions based on predefined roles. ABAC is much more dynamic. It grants access or assigns roles based on attributes of the agent requesting access, the resource, the action, even the environment or context.
Much more granular and context-aware.
Definitely. Think of a placebo pipe as a slot needing, say, a natural language understanding capability. An ABAC-like policy could decide which specific NLU component gets plugged in based on its current measured accuracy, its processing load, maybe its trustworthiness score, and the specific demands of the incoming prompt or task.
So the system picks the best tool for the job at that moment.
That's the idea. We see similar things in cloud platforms like Azure with dynamic permissioning, or tools like Terraform managing dynamic infrastructure roles. This dynamic assignment means your prompt might be handled by the most suitable component available in the meta AI right then.
And this ties into self-optimization. The system learns which assignments work best.
Yes. The meta AI can monitor how effective different assignments are for a given placebo pipe. It can use techniques like reinforcement learning or maybe self-alignment optimization to figure out the optimal instantiation over time.
So the system improves its own configuration.
Right. And formal methods can again play a role by defining the rules or constraints within which this self-optimization happens, ensuring it stays within safe or ethical boundaries.
This self-optimization could mean the system's response to similar prompts changes over time as it learns.
It could, yes. It might find a better internal configuration to handle certain types of requests.
Okay, so summing up the implications for meta AI and prompt engineers regarding these placebo pipes.
First, that need for unambiguous definition using formal methods is key for reliability. Second, ABAC principles look very suitable for managing the dynamic assignment based on context and agent attributes.
Third, self-optimization techniques will likely drive how these placeholders get filled based on performance feedback.
And broadly, we should see these placeholders not just as slots, but as abstract functional roles or capabilities that get filled dynamically by the best available component, guided by policies and optimization. Understanding this flexibility is important when prompting.
Okay, so we have these potentially self-aware components, dynamically assigned roles. How do they all talk to each other effectively? This must require precise communication.
Absolutely critical. Simple data transfer just won't cut it for the kind of coordination needed in a complex meta AI. This brings us to agent communication languages, or ACLs.
Specialized languages for AI agents to converse.
Essentially, yes. They're designed for exchanging complex information, intentions, commitments, engaging in structured dialogues. They're crucial for interoperability when you have diverse components needing to work together, perhaps triggered by one of your prompts.
What are the core ideas behind these ACLs?
The research mentions a few key concepts. One is speech act theory. It treats messages not just as data, but as communicative actions intended to affect the receiver's beliefs or behavior.
Like making a request or informing or proposing.
Exactly, performatives. Another key idea is separating the content of the message from the communicative act itself. This often involves using a content language, like CIF or SL, and relies on shared ontologies or vocabularies, so agents understand the terms used in the content.
So understanding the meta AI's likely ontology could help in phrasing prompts more effectively.
It could, yes. If your prompt uses terms the internal agents understand well, communication might be smoother.
And formal semantics.
Right. This aims to give precise, logical meanings to the speech acts, often based on logics of belief, desire, intention, BDI logic. It defines things like the preconditions for sending a message, feasibility preconditions, and the expected effects on the receiver, rational effects.
Making the communication less ambiguous.
That's the goal. The research mentions two main ACLs, KQML, an earlier one,
Okay.
and FIPA ACL, which is more standardized and has a more formally defined semantics using SL. FIPA ACL is designed for better verifiability, though it can be more complex to implement.
This trend towards formal ACL suggests that prompts interacting with meta AI might also benefit from being more structured and unambiguous.
That seems likely, yes. Aligning with the underlying communication rigor could improve reliability.
It's not just single messages, though, right? There are protocols for conversations.
Correct. Interaction protocols define structured sequences of messages for specific goals. The classic one is the contract net protocol, CMT.
For task allocation.
Yeah, an agent announces a task, others bid, the announcer awards the task, and the winner reports back. There are extensions for negotiation, incorporating norms, trust, etc.
What else?
There are also commitment-based protocols. These are quite flexible. Interactions revolve around creating, managing, and satisfying social commitments between agents, like Agent A commits to Agent B to do X if Y happens.
Sounds more adaptable than a rigid protocol.
It can be, but it needs careful definition of the rules governing these commitments.
Again, formal methods help define and check these protocols.
Yes, formal specification languages like Desire, Z, or others can define the interactions unambiguously. Then, verification techniques, especially model checking, can automatically analyze these specifications to ensure the protocol works correctly, agents follow the rules, and the system has desired properties.
So for prompt engineers, if your prompt needs to trigger a complex interaction within the meta AI, understanding the likely underlying protocol could be important.
It could, especially if you need the system to reliably allocate tasks or manage responsibilities based on your prompt.
How suitable are these different approaches for task delegation within meta AI?
Well, FIPA ACL offers that standardization and formal semantics, which is great for precision and verification despite implementation complexity. Commitment-based protocols offer more flexibility for dynamic responsibilities, but need really careful specification.
And formal specification and verification are needed anyway.
Pretty much essential, regardless of the specific ACL or protocol, to get that rigor. The research also cautions against relying on emergent communication where protocols just arise spontaneously.
Why that?
It just lacks the clarity, verifiability, and interoperability needed for reliable coordination in these high-stakes meta AI systems you'll be prompting. You need clear semantics for defining tasks and integrating responses.
So for meta AI communication, there's a trade-off. Standardization versus flexibility.
Seems so. Maybe a hybrid approach.
Oh.
A standardized core ACL, perhaps FIPA ACL-based, combined with formally specified commitment protocols for more complex dynamic interactions.
And formal methods are non-negotiable for reliable delegation.
Definitely. And commitment protocols seem particularly useful for managing the nuances of delegation, responsibility, and handling exceptions.
Okay, this emphasis on formal specification naturally leads us to the broader role of formal languages in meta AI development.
Right. The research contrasts them sharply with natural languages, like English. Formal languages have strict syntax, unambiguous semantics. They're designed for specific applications, often concise, interpreted literally.
Whereas natural language is, well, messy, ambiguous, context-dependent, evolves organically.
Exactly. And for building complex AI, especially multi-component meta AI, the benefits of formal languages are significant.
Like what? We touched on clarity already.
Clarity and unambiguity are huge. Ensuring consistent interpretation across different AI components is vital for reliable coordination and executing tasks based on your prompts.
What else?
Verification and validation. Formality allows for rigorous mathematical analysis model checking, theorem proving. This helps ensure the system meets its specifications and is free from certain types of errors, crucial for building trustworthy AI.
And automation.
Yes, precise formal specifications serve as direct input for automated tools, code generators, test case synthesizers, automated reasoners.
Knowledge representation, too.
Absolutely. Formal languages like logic or ontology languages like OWL provide structured ways to represent complex knowledge, enabling sophisticated reasoning. The mention of Kiklang for the Hypersia knowledge graph is a prime example of this.
Okay, so Kiklang is likely designed for unambiguous knowledge storage and reasoning in that specific meta AI.
Very likely. And formal languages can also be more efficient for communication between agents, less redundancy, lower overhead compared to processing natural language messages.
But there must be downsides to using formal languages.
Oh, definitely. There's often a steep learning curve. They require specialized expertise.
Right.
Developing formal specifications can take more time and effort initially. Simpler formalisms might struggle to express all the necessary nuances of a complex requirement.
And verification can be hard to scale.
Yes, analyzing very large, complex systems can lead to a state-space explosion problem for verification tools. And perhaps the biggest challenge is ensuring the formal specification accurately captures the original, often informal, user requirements. Getting that translation right is tricky.
So how does this play out in practice? Formal versus informal?
In AI system development, formal methods are increasingly used where safety, security, or trustworthiness are paramount because verification is possible. Informal approaches are more prone to ambiguity and errors. Interestingly, AI is also starting to be used within formal methods development, AI for FM.
Okay, and for agent communication?
Formal ACLs are generally preferred for agent-to-agent communication within a meta AI for clarity and coordination, though highly structured formats derived from LLMs might also offer efficiency. Informal natural language is still essential for human-agent interaction. Obviously, that's where your prompts come in.
So the implication for meta AI seems to be
A strong need for formal languages in core components. Knowledge representation like Kiklang, planning and reasoning modules, the communication protocols we discussed, the complexity and reliability requirements demand it.
but probably not everywhere.
Likely a hybrid language strategy. Formal for critical internal functions, perhaps less formal or natural language for human interfaces or less critical parts. Bridging that formal-informal gap is an active research area.
And using formal languages enables things like automated reasoning over knowledge graphs, formal verification of properties, structured self-monitoring or explanation.
Exactly. Those advanced capabilities rely on that formal underpinning. And the efficiency gains for internal communication shouldn't be underestimated either, especially as these systems scale up.
Okay, so we've got these complex systems with self-awareness, dynamic roles, formal communication. How do we actually know if a meta AI is working well? Is it effective? Is it cohesive? This leads to evaluation.
A huge question, right? For developers and for users like prompt engineers, how do you measure success?
The research defines effectiveness fairly intuitively, achieving goals reliably, accurately, efficiently. What about cohesion?
Cohesion is more about the internal workings. How interconnected, aligned, and consistent are the interactions between the components? Do they function as a unified whole? It draws a parallel with human team cohesion.
So how do we measure these? What metrics are useful?
We can borrow from several fields. Multi-agent systems,
Yeah.
MAS research, offers performance metrics, task completion time, success rates, throughput, resource use.
Standard performance stuff.
Yeah, but also scalability metrics, robustness, like how quickly it recovers from faults adaptability, and crucially, coordination metrics. Communication efficiency, decision synchronization, how well tasks are allocated, measures of cooperation.
Okay, what else?
We can also look at knowledge similarity between agents if they maintain separate knowledge bases. How aligned is their understanding?
What about from other fields? Distributed computing.
Right. Distributed computing and CSCW computer-supported cooperative work. They have frameworks looking at the task, the group, social protocols, technology. Metrics include interaction patterns, how shared information is handled, like concurrency control, standard performance measures like accuracy or precision, but also process metrics like coordination overhead.
Awareness metrics too.
Yeah, social awareness, workspace awareness, situation awareness, how much components know about each other and the environment.
And you mentioned human teams. What can we learn there?
The concept of team cohesion is really relevant. It's defined as this dynamic process of members sticking together for objectives or needs.
Dimensions like task cohesion and social cohesion.
Exactly. Task cohesion is about shared commitment to goals, seems very applicable to meta AI alignment. Social cohesion is more about interpersonal liking, bonding. Research shows task cohesion in particular links strongly to performance.
How could we measure that in a meta AI?
We could adapt the concepts. Assess task cohesion by analyzing execution traces. Do agent actions align with the overall objective, maybe set by a prompt? Assess social cohesion by looking at communication patterns, stability of interactions, maybe even agent self-assessments if they have that capability.
Interesting. And if humans are involved, human AI teaming.
Then HAI metrics become vital. It's not just about task outcome, but the quality of the human-AI interaction.
Like trust.
Yes, trust calibration. Does the human trust the AI appropriately? Transparency and explainability of the AI. Adaptability. How well do human and AI adapt to each other? Shared mental models. Do they have a common understanding? Human satisfaction, collaboration, effectiveness.
Complementarity too,
Well-
using the strengths of both.
Right, leveraging what humans are good at and what the AI is good at. Evaluation frameworks here often depend on the specific mode of collaboration.
Finally, software architecture principles. Coupling and cohesion.
Yes, these are classic software engineering concepts, but very applicable. Coupling measures interdependence between components or modules. Lower coupling is generally better, makes the system easier to change.
And cohesion.
Cohesion measures how functionally related the parts within a single component are. Higher cohesion is usually better. The component does one thing well.
So, for meta AI components,
You'd ideally want high cohesion within each individual AI agent or component and low coupling between them. This promotes maintainability, understandability, robustness, scalability, all good things for reliable responses to prompts over the long term.
so evaluating meta AI needs a really broad toolkit.
Absolutely. It's multifaceted. You need MAS performance and coordination metrics, architectural metrics like coupling cohesion, maybe adapted team cohesion concepts, and if humans are in the loop, definitely HAI metrics. The overall effectiveness relies heavily on that internal collaboration quality.
And that idea of task cohesion seems particularly relevant for prompt engineers, ensuring all the internal parts are actually working towards the goal defined in the prompt.
Precisely. And those architectural principles, low coupling, high cohesion, are fundamental for long-term system health and predictable behavior. If humans are involved, metrics like trust and transparency are non-negotiable for a good interaction.
Okay, building trustworthy AI, that brings us squarely to ethics. How do we integrate ethical principles into these complex meta AI designs?
It's not just an add-on, it has to be foundational. Given the potential impact of these systems, ethics is imperative. We're talking machine ethics or computational ethics, designing AI that behaves in morally acceptable ways.
And again, formal methods seem important here, not just vague principles.
Exactly. The research strongly advocates translating ethical principles, fairness, non-maleficence, transparency into precise formal rules. Natural language is too ambiguous for this.
What kind of formalisms?
Deontic logic is a key one. It deals with obligation, O, permission, P, and forbiddenness, F. You can use it to formalize norms. For instance, an axiom stating it is forbidden, F, to use attribute X for decision Y to enforce fairness.
So expressing rules like don't be biased.
In a much more precise way, yes. Temporal logic is also useful for reasoning about ethical properties over time, like bias must not increase until a fairness intervention is active.
Okay.
Other logics, like continuous logic programming, can help balance multiple objectives and constraints, which is common in ethical dilemmas. The focus is often on system-level specifications governing the overall meta-AI behavior.
How do you represent these rules? Where do they come from?
They often draw from established ethical theories, consequentialism like utilitarianism, maximizing good outcomes, deontology, rule-based ethics like Kantian principles, virtue ethics, focusing on moral character.
And you encode these as formal rules.
Yes, as logical axioms, constraints, optimization objectives like maximize expected utility subject to fairness constraint X, or rules forbidding actions based on sensitive attributes. Argumentation frameworks are also mentioned, representing different ethical viewpoints as arguments and counterarguments to reason about conflicts.
And can we automatically check if the system follows these rules?
That's a major goal. Automated verification techniques, theorem provers, model checkers can analyze the system design or behavior against the formalized ethical specifications.
Like an ethical check.
Essentially, some research proposes architectures like an ethical firewall that embeds verification and auditing capabilities. You can also evaluate outputs at runtime for things like bias, fairness, harmful content.
What about when ethical rules conflict? Dilemmas.
That's notoriously hard. Approaches include using those argumentation frameworks to resolve conflicts based on specified preferences, setting explicit prioritization rules, trying to learn ethical preferences from data, with huge caveats about descriptive versus normative ethics.
Learning ethics from data seems risky.
Very. Other options include randomization in tie-breaking situations, allowing agents to rebel against unethical commands if specified, and crucially, always maintaining human oversight and accountability. The AI can assist, but humans must remain responsible.
How does this connect to trustworthy AI more broadly?
Ethics is really at the core of trustworthy AI, alongside other pillars like validity, reliability, safety, security, resilience, transparency, accountability, explainability, privacy. Formalizing and verifying ethical constraints directly contributes to trustworthiness.
And governance frameworks play a role.
Yes, guidelines from organizations like IE, the EU, ACM, plus standards and risk management frameworks like the NIST AI RMF provide structure for implementing ethical AI.
So for meta AI, the implications are
Formal methods like deontic and temporal logic seem necessary for rigorously specifying ethical constraints and enabling verification for trust. Ethics needs to be considered at the system level, governing interactions between components.
argumentation frameworks could help manage conflicts transparently.
Right, and the traceability you get from formal logic and verification provides a strong foundation for ethical explainability, contributing to transparency and accountability. You can point to the specific rules and checks.
Okay, one last major area, the overall architecture. Centralized versus distributed control for these meta AI systems.
A fundamental design choice with big trade-offs. Centralized means one main controller, global view, command subordinates. Decentralized means control is spread out, agents act on local info, interact directly, global behavior emerges.
What are the trade-offs? Centralized sounds simpler, maybe?
It can be easier to achieve a globally optimal solution because one entity has the big picture, but it creates a bottleneck and a single point of failure. Scalability can be limited. It's often less flexible or adaptable to rapid changes.
And decentralized.
Generally more robust, no single point of failure. Often scales better because work is parallelized, more adaptable as agents can react locally, But achieving coherent, optimal, global behavior can be much harder. Coordination is complex. Real-time responsiveness might be better locally, but overall coordination takes time.
So neither is perfect. Are there hybrid approaches?
Lots of them. Hierarchical control creates levels of agents of balance, but deep hierarchies can introduce delays. Centralized training, decentralized execution, CTDE, is popular in multi-agent reinforcement learning. Learn coordinated policies centrally, but execute them decentrally at runtime.
Interesting. Learning together, acting alone.
Kind of. Market-based control uses economic mechanisms like auctions for decentralized task allocation, can be scalable and flexible, but might only find locally optimal solutions. Holonic architectures view agents, holons, as both autonomous wholes and dependent parts of larger wholes' self-organization within a structured coordination framework.
Lots of options.
Yeah, and even just mixing centralized and decentralized protocols for different aspects of coordination.
So for meta AI architecture,
Yeah.
what's the likely path?
There's no single best answer. It depends heavily on the scale, criticality, operational context. You have to balance those conflicting attributes.
Hybrid seems probable.
Very likely. You might see centralized components for high-level planning, ethical oversight, or resource allocation, combined with distributed, specialized agents for specific subtasks like data analysis or language generation. Hierarchical, CTDE, holonic models all seem relevant.
But effective coordination mechanisms are key, regardless of the pattern.
Absolutely paramount. How information is shared, tasks are allocated, conflicts are resolved that needs careful design, whatever the high-level architecture.
And for really complex problems or large scale.
Decentralized elements seem crucial for scalability and robustness. A purely centralized meta AI would likely hit bottlenecks and be too fragile.
Okay, we've covered a huge amount of ground here, from AI self-awareness and metacognition, through formal methods for placeholders and communication, the role of formal languages, evaluating cohesion, integrating ethics, and architectural choices.
It really shows how interconnected all these aspects are in designing these advanced meta AI systems.
And for you, the prompt engineers listening, the key takeaway is that understanding these deeper layers, the AI's potential self-awareness, its communication protocols, its internal structure, can directly inform how you craft more effective, more nuanced prompts.
Definitely. Knowing an AI might self-evaluate could change how you ask it to check its work. Understanding its communication structure might suggest phrasing prompts more formally or clearly for delegation. Awareness of ethical frameworks might guide you to prompt in ways that align with its embedded principles.
So here's a final thought to leave you with. We see this need for both rigorous formalization and adaptable intelligence in meta AI. How might prompt engineering itself need to evolve to bridge this? How can you best leverage these sophisticated capabilities like self-awareness or formal reasoning while also navigating the ethical dimensions of interacting with such powerful systems?
Yeah, what new skills or deeper understanding might you need as prompt engineers to really master interaction with the next generation of meta AI? It's something worth thinking about as you continue your work. We definitely encourage exploring the research further if any of these areas sparked your interest.
Absolutely. The landscape is changing fast, and understanding these foundations seems crucial.